Great. So I can skip a lot of the conceptual parts just because that takes time and it's intuitive. I think as soon as you watch that video, it will be helpful. I will be basically repeating the same thing. So we can save some time here. Today's topic mostly is Adaline. Adaline, the process of Adaline model is going to be very important and useful, because once you understand Adaline and how to do it, you'll almost surely, will understand logistic regression with just one tweak. And I'll talk about that tweak. I'll highlight that. And once you understand logistic regression, to add regularization, just 2 tweaks. So Adaline is the very fundamental part. You want to make sure there's no errors in the process. You want to make sure you can get the same result that I have here in the demo or in the video, and be familiar with the process. So that's the main content. And above that, between Adaline and logistic regression, we have, again, we do train test split. This time we split both X and Y. We separate X and Y before we split, and then we split. We get 4 sets of data, and I see the hand. And we'll do a quick hypothesis testing. Instead of doing it for all the variables, one test is going to be very, informative. And then do the data pre-processing. And this time we'll not do the manual process where we do step by step, but this time it's a more automated process, which is called column transformer, or another way to say it is more of like a pipeline process. Then above the model, it's the regularization, and a few kind of technical points like sigmoid function and clipping, and learning rate, right? And maybe regularization parameter, which is another scaling point. Question? Last semester, the other course? Yeah, we did logistic regression and linear regression, k-nearest neighbor. Yeah. Great question. Logistic regression is often seen as part of as a type of linear regression. They do share similarities, but the learning process is kind of different. That's the point where linear regression diverges from, or neural network models diverge from linear regression. That's where the diverting point is, I believe, logistic regression. So once you know logistic regression, you're closer to understanding neural networks than regular regression. In the case of regular regression, there isn't really any learning going on. It's one-step estimation process. That's linear regression. So you will not have this iterative process as we will see here. And with k-nearest neighbor, it's even farther away from machine learning. It's more of a lazy learner, as we call it. So to, sort of at a higher level, they are different machine learning models. But in terms of, you will put them in different, different beings. Linear regression, k-nearest neighbor, they are strictly linear models. You label the bucket. It's linear models, strictly. Logistic regression, neural networks, and artificial, I guess, models or neurons, these are nonlinear models of a unique kind. And on nonlinear models, you also have decision trees, tree-based models like forest and things like that, and another bucket. But inside that nonlinear model bucket, strict comparison, nonlinear model is more powerful than linear models, basic. But in that nonlinear model bucket, there are many, many kinds. And neural network model is one of the most black boxes, I would say. If you compare, some are less black, the other are more black. Neural networks are more black. That's why we focus on here. Once you understand that, I wouldn't say there's any other model that you couldn't understand. So that's why we focus on that. Make sense?
So that Adaline model is
right. Adaline model is a stepping stone between the linear to the nonlinear that helps lay the foundation in terms of understanding. Once you know that, with one tweak, suddenly you're crossing the line to nonlinear models.
the similarity in that it has a reduce that
Yes.
learning.
Right. Yeah. Great. Those are great questions. So, right. So that's it. And before I talk about today's content, I would like to mention this. I mentioned it to some students, but not in the class. I will slowly bring our senior students back into the classroom virtually, mostly because they are not in Houston. Some of them are. Lily is here, and thanks to Lily, she will be the first one to talk about her experience in terms of interns and jobs. And so that's why the first one will feature Lily. And typically I invite students live to the classroom and talk about their suggestions and experiences. I ask a few questions. They'll follow a format, and it would probably take 15 or 20 minutes. But there are circumstances we cannot do that. So Lily has already done a video interview with me. I recorded it. I'm in the process of finalizing the editing. Once I finish that, I will put it on somewhere that you all can see, right? And so you can see it offline. I will not play it in class because it's not a good use of class time. But special thanks to Lily. She's sitting there. And I should be able to post that link or video either tomorrow or sometime later this week. And also congratulations, she got a full-time job extension from the same company that she talked about in the video. So, be prepared for, hearing a lot about how awesome Bauer is, and and then I've already contacted Emat, who's working for Tesla. He will join me if everything goes well. He will join me next class, in class live. He will talk to us, okay? And at least one or two other students are in the plan, potentially Sahitia, if you know her, or maybe Sophia, if you know her. Sahitia is joining HP, I believe, and Sophia has interned with Houston Symphony, one of the big nonprofit organization in Houston, which also has a national stage. So that's the current plan. Let me know if you have any thoughts or any other students you want to invite that you have a relationship with. There will be good ideas. If we cannot do that this semester, we can do it next semester. we can plan for it. All right. So these are more conceptual points, but there's something I want to mention here. The this would be a generic form of 3 different layers. We have an input layer with input data. We have a kind of the black box in the middle, hidden layers. Sometimes this layer can be huge, 12, 18 layers. So complex, I cannot understand how that works, but I can still put it to use. And then we have the output layer. The input and the output are more transparent. You know, you have to have good control of them, but the hidden layers are where the power comes from. And for the different models, for between Adaline and logistic, really the difference is here. This is what we call activation. The way activation happens for Adaline, call it A, is it literally does nothing. It's linear activation, which means you multiply that by 1, which does nothing. But we do that instead of skipping that step, because we know that when we do the logistic regression, we will do something here. This is kind of, how should I write it? Linear, times 1. But logistic regression use a sigmoid function. So when you adapt the codes from Adaline to logistic regression, you will rewrite that line of code and copy everything else. That's the only difference. So, and this S shape is most likely referring to logistic regression and the sigmoid function, which turns a real number line, the x-axis, into an S shaped activated values. At the middle, it should turn it to 0.5. And, it's a monotonic increasing function, which has very nice mathematical features for this purpose. But another thing that you may have heard about or will hear about that shares the same shape, but with the only difference is the range of the activate value. It should be 10h. The other function is 10h. Tangent, hypertangent function, which converts the real number line into number between minus 0.5 to plus 0.5, something like that, maybe, where the middle point transforms the value from 0 to 0. So that's more of a symmetric, where you have between 0 and 1, and the midpoint is 0.5, which is kind of odd. The other hyperbolic tangent, something like that, it transforms to values where it has a mean of 0. So that's kind of symmetric. But that's more technical difference. Either function work similarly well, I would say, in machine learning models, but in the state-of-the-art models tend not to use any of these. It uses ReLU. We'll talk about ReLU when we talk about neural networks. ReLU has odd shape, but it does really work well and better than sigmoid. The reason it doesn't work that well or compared to ReLU is because when you calculate the gradient, it's harder for this function because this function is more complex. And calculating gradient is an important step of the calculation process when it calculates the optimal weights. So that's why. That's the only point I want to bring out here. A lot of notations, I'll try to, emphasize them or kind of point out what you really want to pay attention to, or you want to make sure you understand. I will point that to you. These are all talking about the background. Important difference between Adaline and a version of the learning algorithm before that is that Adaline improved the feedback learning process by avoiding a step function, a rigid step function, and with a linear function, which, if you compare the difference here with the perceptual learning rule, it's instead of feedback the learning, which is what we call backpropagation in neural networks, instead of form the error based on after the step function, it formed the error from in between when the function is still a linear or a continuous function. And the good thing with that, and Adaline adds a step which does nothing, a linear transformation. But this is more of a placeholder to later be familiar with the structure and only replace with the function to make it logistic regression. And with that or without that, the process makes backprop and gradient descent much more feasible. It makes it possible to find the best solution. With here, the solution will be unstable. That's the only difference. Okay, and now, in the reason we talk about Adaline, I said, is to make it easier to transition to logistic regression. Logistic regression is really the objective here, but learning Adaline simplifies one step, but all the others are the same. It makes it learning easier. Once you learn that, transition to logistic regression is even easier. And here it compares the difference. The difference is the activation function, right? And with this difference, you only need to understand what sigmoid function is. How does it transform value between the real line and the confined space? And why does it do that? And after that, you only need to know the formula for the transformation. So that's that. And now we're really getting into the technical sides where we will talk about, okay. Let me change the pen. So we'll talk about these steps. You'll see me refer to these notations. The cost function, I will use J of W, where the function depends on W. W is the weights. Weights is the only numbers we can change, we can manipulate here in order to improve the model. We cannot change data. Data are data, right? And once data is in the proper form, we don't change it. Otherwise, we're lying to ourselves, right? We need to be honest with the data and change the model. The model essentially is a bunch of weights, and weight is denoted by W. This is also sometimes called loss function. And this is the objective that the model tries to minimize. The loss function is something that we deserve to be, that we want to be smaller. Smaller the better. And in classification problems, especially binary classification problems, we will calculate what we say sum of squared error. Sum of squared error is perhaps the best way to quantify the amount of errors that the current model is, I guess, is experiencing in terms of trying to classify the data. To estimate the distance between the current model and the best model possible. The best model possible potential has 0 sum of squared, where it has no distance between classification and the actual truth. But model almost always will make some mistake because of the randomness of the data. A perfect model does not exist, but we do have the best possible model. Sum of squared, when you calculate, is we would add the amount of error on each of the training example, add them together. So we will have as many as n data point. Each is denoted by I. It's the distance between the true value of y for that specific training sample, between that value and the activate value of the point. We'll talk about this z. Z is the step before. Z is the step before activation function, and this phi symbol is the activation function. When you calculate the distance between the actual label, let's say for binary classification, it's 1 or 0. Sometimes people use 1 or -1. It's trivial. It's not really making any difference as long as they're different. And the scale does not matter that much. If we use 0 and 1, then let's say if this case has a true label of 1 and the activated value is 0.9, then the error here is 0.1. The error points to the direction where the model could be improved to be closer to the true value. So it's always true value minus the activated value. And this is the prediction error for this particular data point. When you take the square, it's a squared error. And when you sum everything together, that's a sum of squared error, right? So that's a cost function. Our purpose is to minimize this. Obviously, you cannot change y, but you can change z. And z essentially is combining data and the weights. You cannot change data, is the input features. You cannot change data. You can change the weights. So that's why weights are the only thing that we will change here in order to improve the model. And what's gradient? We'll talk about gradient. Gradient is the slope in multi-dimensional space. The slope of the loss function with respect to the current value of W. nonsense. Later, I'll draw some graph to kind of illustrate what that means. But if you think of gradient as the rate of change, which is the slope, right? The rate of change of the loss function at the current point of the weights. The rate of change of the loss function at the current point of weights. That's a gradient. And gradient helps to find the delta W. Help us find how much change do we need to apply to the current W to improve it, and in what direction. That's the purpose of gradient. All right. Enough of technical. Let's talk about the codes. So that's a process. I'll refer to this process when we go through the steps. When we go through the codes. I'll be talking about these mostly referring to the homework. Right, homework 2. Homework 2 will ask you to do some data preprocessing, and you'll do a complete loop process, one loop of the Adaline model. After that, you'll do you'll put them together and change one thing to make it logistic regression, and run the loop directly. And after that, before logistic regression, you'll use a different approach to preprocess data, which is the column transformation. And after that, you do the logistic regression. After that, you'll take the codes of logistic regression process and change two things to add regularization to the model. And in the end, you'll use the regularized model process to, after it's being trained, to make predictions and calculate the accuracy on training and testing sets. Right? So that's a complete process of the homework. And these two, I will suggest that you print them out to have them handy. If you like working with a screen, for sure you don't have to print them out to save some trees, but it's a personal preference. And this is more of a list view of the process. This is more of timeline view. This part, after this step, don't forget that this step is here, and the notation is here. It's hard to put them really neatly. I mean, I think this is the least messy state I can make it, and it's still messy. And I like to be more cleaner, but I cannot improve it anyway. And by these are cheat sheets. These are cheat sheets. So this process is more conceptual, and based on that, I have notations. Notations are exactly cheat sheets, where if you understand the process, then these notations are codes. And this is code, right? So when you don't, as a reference, when you forget what to use, and if you're lost in a notebook, I mean, let's say you have your homework, you open the homework, you're kind of lost. What's this? This is to help you get a high-level view of the process and know where you are, right? And it can even replace the videos. So when you practice the process, when you watch a video and work on the notebook, try to build this resource into your process, so that eventually, I think you can live without the videos. Everything that you learn from videos when you work on these problems, you can add your annotations on this to build onto it, right? To add your, I guess, interpretation of the process. If the video talks about it, but I didn't add it on it, these are bare minimum of the notes that I think should be included. That's helpful. But this is more of a cheat sheet, right? Cheat sheet with directly useful, not only conceptual, but directly useful resources that you can simply bring to the exam and copy, and should work. Okay, and the videos I'm talking about is the homework assistance videos. Great. Before I dive into the codes, let's take some kind of break, switch gears, and let me ask you a few questions. You know the drill. All right, so it's gonna be interesting. It's gonna be more intensive this time as we get to more technical concepts. And we didn't have a class last week. We did have an interesting session where I demonstrated notebook and coded a few lines just to show the process of me working on notebook, so that maybe you can pick up a few tricks, like shortcuts and things like that. It's a fun journey where the process of coding becomes more and more and more enjoyable as you be familiar with the tool. It's deep. I'll never imagine a state where I'm like optimal. It's not going to be an optimal state, because as soon as you get comfortable, it changes. But it changed for a good reason. The design changes a little bit. You have to adapt your routine. But it's a fun journey. And okay, so this time, I'll ask the question. I'll ask you to raise your hand instead of scream the answer, because it's more complex answer. It's something I will not be able to distinguish when many students scream. And this time you want to think clearly, because for the first question, if you raise your hand and I pick on you and your answer is incorrect, there'll be penalty. But small penalty. But when you get it right, of course, good reward. Okay, the first one. When I describe the data, the format of the data, it's a matrix, right? And I often use N and M to refer to sides of something. And my question is, when I say go, raise your hand. Don't do before that. I'm gonna pick on the first hand, okay? But not any hand before I say go. And don't scream. Which one of these symbol is that I use to refer to the total number of data points? Go. Anyway, so I know who the first hand is, but the question is, which one of these two symbols do I use to refer to the total number of data points? I think Maria, Abby. Well, what's your name? Sorry. You got the question. Yeah.
Well, already answered the question.
You did?
Yeah.
What did you say? Did you say it out loud?
Oh, I did the Alexa series. Much easier than this question. So here's a penalty I don't want to answer because I already know.
What's a penalty? That's a good question. I didn't think it through because I thought nobody will answer. Well, and given your confidence, I don't think you should be worried about that. So give me the answer.
So you said the total number of data points?
Yeah.
I think it's N, because I have it in my notes.
Yeah, as in Nancy?
N is in Nancy.
Okay.
Yes.
Yeah, that's correct. So no worries about penalty. And just a follow-up question, no penalty, maybe reward. What's M? Huh?
Like real variable.
Number of input features.
Yes.
Yeah. So when we have a, which I kind of have it here. So N, when we write the data set in the form of a matrix, N refers to the number of rows, which is the first dimension of the notation when you slice the data point. When you slice the data frame, N is number of rows. It denotes the number of data points, the number of training examples, or sample size, different ways of saying it. M is the number of columns of the processed data set or pre-processed data set, which is ready to be fed into the model, which is the width, number of columns, number of training features, number of input features, number of input variables, which includes all the flag variables that you would make after you transform the categorical variables, not only the one column of categorical, but all the flag variables as a result. So N by N, we'll stick to these notations. And typically I will use I to refer to one example of the data point. I will use J to refer to a specific feature at a time. And these notations are necessary because sometimes we write formula to illustrate one point. Great. Can you remind me one more time your name?
Jordan.
Jordan. Okay. I'll definitely remember.
Yeah, sorry, I'm sitting this side.
That's fine. That helps me. Where's my pen? All right. So I guess double reward.
No, that's okay.
You want to give it to somebody else?
I've got like 6 friends here.
You probably don't want to answer that question. Okay, great. Here. Wow. All right. The next question. Can you use an example? Can you explain the purpose and then use an example, either that we talked about in the course or don't have to be, but as long as it makes sense, to explain what a z-test is for? Go. I guess Jordan again. If
The Z-test is testing for
example.
Oh, sorry, example. Sorry, I'm directing wrong.
No, yeah. Definition first and then example.
Yeah, no, I'm both. I got the definition.
Yeah. Yeah, go ahead with or somebody else with a given example. Example of conducting z-test and illustrate how the process. Valerie? In terms of yeah, let me ask a follow-up question to zoom in. In terms of proportion, can you name an example in terms what does the proportion mean, or what does it refer to? Yeah. Okay, I think there is a confusion there, but no penalty in this case. Brave enough. So the proportion that the z-test is testing for is not the proportion where you split the data set. That is entirely independent topic, although they happen to have the same, I guess, way of saying it. Here, the proportion that the test is testing for is referring to a different thing. Lily?
I wanted to double check. I didn't want to answer the question. Just double check that are we using just for categorical variables and t-test for numeric variable? Am I right? Or
Yes.
okay.
Yes.
So yeah, so we're going to use a proportion instead of equal mean because we're going to use equal mean for the numeric variables, and we're going to use the equal proportion for the categorical variables that we want to, we want to test if this is null hypothesis is correct or not. That we can reject it or we cannot reject it.
Okay. Yeah, yeah. And hopefully that illustrates the point of testing the hypothesis in the same place. The purpose of conducting hypothesis testing on the train and test sets is to make sure that they are similar on key properties of the data set. The key properties of the data sets are essentially the input features. There are systematic features, there are randomness features. We want to make sure the systematic features are the same in terms of, for testing purposes, right? For testing purposes, let's say you build a car for this road for the car to achieve optimal speed. Then now you want to test it. When you test the car on the same road, of course it's going to do well. You want to test it on a different road. But you also want to make sure the other road is a fair testing environment. That's the purpose, right? How to make sure the other road is the same test environment. You want to make sure the slope are the same. You want to make sure the pavement are at least comparable. They don't have to have the exact number of dust points on the road because you cannot make sure that happens, but at least they have to be comparable, right? You cannot build the car in the roads that are in, I don't know, in Texas, and then test a car in Russia in winter on icy roads. It's unfair, right? So that's a key properties of the testing environment that we're talking about. In terms of data set, the testing environment are essentially the variables. They want to make sure that the key statistics of those variables are the same, are not exactly the same, but statistically non-differentiated. And hypothesis testing is a way to make sure you can call them the same, right? Valerie?
Follow-up question. Does it mean that the hypothesis
Yeah. Right. For rigorous, I guess, diagnosis, it would test for each of the variable. And the reason we need two kinds of tests are because we essentially have two kinds of variables. We have numeric variables that can take any value, decimal points, and we have those kind of variables that have only a few, unique values, like gender. So t-test is suitable for numeric variables, and which we call interval or continuous variables, like age. You can potentially, have a wide range of age values, but we also have z-test for the categorical variables. Yeah. Make sense? Yeah. Yeah. Gender, or anything that you can call categorical variable, like geographic area, yeah. So, okay. So these are the questions. These are more technical, but these are, I guess, relevant to the homeworks at least. And the tests are directly related to homework and an exam, and the other are just, I guess, key technical elements. Okay, so let me dive into the process here. Before the loop, and after we have the data ready, let's say we have a prepared data set. At this point, I didn't split the data into train and test. Here, the purpose is to illustrate the process. For Adaline, we don't really have to split because we're not trying to test the performance of Adaline, but we're trying to learn the process. So we only have one data set. Let's call it train. With the train set, the first step, even before the loop, is the loop where it's the area outside the loop is where we prepare a few utility variables. We need to prepare data set on one side. We need to have the learning rate, which is just a value, a fixed value that we pick. We need to have a placeholder for the weight, delta W, weight change, right? I believe that's mostly it. What else? Yeah, and then we start the first loop. Inside the loop, you'll calculate the net input, and it's called decision process. You wonder why it's called decision process? Calculating z is the net input. We call it net input. This step is called decision process. Why do we call it decision process? The reason we call it decision process is it's essentially doing a forward prop in the terms of neural networks. At this stage, we don't say it out loud, but eventually you will be familiar with that in the neural network concept. Forward prop is when you try to make a prediction, try to make a classification by using the current weights. You calculate z, which is a linear combination. We call it linear combination or linear input, which is a net input. It's a linear calculation process between the weights and the data that's associated with the weights. Everything here is linear. It's taking inner products of the matrix, which is a bunch of multiplication and the summation process. And it's a decision process because the model, because you're essentially trying to predict the outcome by using the current model, current weights. And that's what model does when eventually the model is trained. Forward prop is the process where you take the model to make a prediction. That's the first step of the prediction process. It's forward prop. After the optimization process, you have a model ready. You want to predict an out of sample case. You go through a forward prop. That's it. So that's why it's very similar to the decision process. Think of a scenario where you make a decision. You want to purchase a product on somewhere, and you will go through this comparison process. You search for the product, you see a few options, you try to decide which one provides the best value, which ones are, I guess, too expensive, you'll rule out. You go through these different steps, but within each step, you'll go through some kind of comparison calculation to make some decisions. That is, this process is kind of similar to the decision process, where it calculates the raw inputs. It calculates, based on the raw inputs, it calculates a kind of a ranking system where you pick the best option. So that's why we call it decision process. Hopefully it's intuitive. Then after you have the Z, you'll go through the activation. I think it's better for me to do that with the code. So here's the initialization process. We need the data. We need a data set, and we also explicitly calculate the N and M, two values that we'll refer to in the process, I believe. Do we refer to that? Maybe we do some sanity checks with that. And we need the number of epochs that we repeat the for loop. The learning rate we have to specify, and then we randomly generate the weights. By randomly generates the weights to provide the starting point, but it's the worst model possible. Let's say it may be the worst model. It's a random model. We have to start somewhere. We also have a placeholder for delta W, the weight change. The reason we need that, there should be some way to not having that at the beginning, but the reason we do that is because in the weight vector, we do have two kinds of weights. Most of them are the weights associated with the data, and there's one special weight, which is the bias. It's similar to the intercept term, which is not associated with any specific inputs, but it's there for a purpose. We include it in the same vector to keep things clean, to avoid defining two things. Because in the net input, we can simply use one vector to do the calculation instead of doing two. Instead of you have to join them. So that's why do that. But the weight update calculation is kind of different for the two kinds of weights. So that's why we have to have a placeholder there to store the weight update in 2 steps. Anyway, and print the output, make sure when you do the code, you get the same numbers. Otherwise, you cannot compare the ultimate results. Okay, now, so I was talking about weight. I will talk about net input. So net input is the combination between data and the weights. So that's what we see here. We have a matrix calculation and an addition here. Here, you can see what the structure is in terms of the weight factor. It's kind of odd, a little here. The weight, I'll say ode. Ode is the, let's say weight ode is the current weight. When we have the weight update, we combine the old weights with the weight update to become the new weights, but then we replace the weight old, the old weights immediately. We cannot only keep one copy because you have to overwrite, right? So we have W old. We use that. We treat it as the current weights. But when we have an update part, like +1, we calculate a new weight. We keep that old weight on the side. We calculate the new weight by plussing 1. And then as soon as we calculate the new weights, we update the old weights to be the same as the new weights. Just so that we can, if you do debug in a middle point, you can compare the old weight and the new weight. If you instantly overwrite old weight, there's no way to compare what was there because the memory is wiped out. This is for, it's more technical.
And then when it's done, you put it on the old.
Yes. But then you can do diagnosis.
You have 2 at one moment.
At one moment, yes. But at the moment before that, you have 2 different versions. Yeah. Ultimately, the new weights there is kind of a spare. It's a temporary thing. Weight old would be the ultimate, updated weights that we stick to. Okay, so more important is the structure of that vector. There's a first element. It has index of 0. This is the index of the weight vector. So we have m features. Each feature should have a weight, right? And so m features. The first is bias. Always we keep it first. Just like intercept, we always keep it at the first with subscript 0. Here it has index of 0. And so this is the weight that corresponds to the first feature. And of course, the second, and then the last one. So the last one will correspond to the nth features, or mx. Can anybody tell me the index for the last element? If you want to slice the last element or select the last element of this vector, which index would you use? 0, 1, 2, something here. Of course, but to be more precise, yeah. I heard M, I heard m plus 1, m minus 1. So we have m or m minus 1. How to know? One way is to kind of see the I guess symmetry of structure. We have the first one referring to bias and it has index 0. The second element has index of 1 corresponding to the first. Index 2 corresponding to the second. 3 to the third. So we have m to the mth. That's m. Right, so that's right. And so with m, how many elements are here? M minus 1? Any other opinion? M plus 1? M plus 1. We have from first to the m plus the 0. That's m plus 1.
The bias also has an element.
Right, it's one of the elements. Yes, so that's where the confusion comes. So it's important to kind of make it clear. The length, if you say shape, if you run this code, it will return m plus 1, and the other dimension is 0. So it's a vector. So it's important to realize when you have W owed and you select 0, it's referring to the bias. When you want to refer to all the other weights, you will do slicing notation, which begins from the second element, which has index 1, all the way to the end. How many elements are in there? M. And that corresponds to the number of columns of your input data set. That maps. Calculation can proceed in that way. Otherwise, it will give you an error. So that's why when we do the dot multiplication, we have x dot multiply weight beginning from 1. So when you have x, the shape of x is m by m. When you dot multiply with w of owed from index 1 to all the way to the end, it has a dimension of m to nothing. So you are multiplying a matrix which has n by m multiplied by a, let's say it's a it's a column vector that has only one column, but so that these two can match. When they match, it can calculate. And in the end, you have as many rows as n, but as many columns as 1. So it's a column vector. So you start with a data set that has n rows, m columns. Through some calculation, it becomes a column. It has n rows and 1 column. So, what did it go through? The number of rows didn't change, which means person 1 is person 1. Person 1 remains person 1. Person I remains person I. All the calculation is happening inside the example. And what goes away? All the different features are lined up with all the different weights, one by one. We're doing an inner product, implosion sort of. We multiply the weight with the corresponding input. We multiply the next weight with the next input, multiply that, and add them all together, becomes one number for each example. That's what happens. Isn't that a linear regression, right? For every example that's a linear regression, you multiply the weight with the input value, do everything for all the features, and then you add them together. That's the linear regression. This is conveniently done by matrix calculation. So that's the first part. And after that, you add the weight, you add the bias to every term, right? To every training example. So this is more like broadcasting. This is a column vector, and the last one is the bias. When you add a scalar to a matrix, you basically add the scalar to every element. So you don't have to make a column vector. When you do the plus, you can do that. So so you can imagine for every element of Z is a column, by the way, right? For every element of Z, it has already considered all the data points weighted by the corresponding weights. It's a linear combination of the inputs weighted by the corresponding weights. So here the weights are critical to dial up or down a particular feature. If we have a feature which is age, if the age is very important to predict the outcome, then the model will learn through iteration that the weight for age should be larger. Then when you calculate Z, it will dial up the influence of age. For the other input variable, if it's not very useful, informative, you don't have to exclude the variable. The model learns to dial down to over time to update the weights to be very close to zero. If the weight is very close to zero, regardless of what changes is there in that variable, it's not going to make an effect in the way that you predict the outcome. That's how the model select which features will make a bigger influence in terms of prediction, right? You don't have to. That's why we don't have to manually remove variables. Model has a way to do that. It will learn and update. But we began with random weights. The model is random, right? But we will learn how the model will update itself. So activation. Once you have the linear input, it has to go through a nonlinear process to realistically make a decision. So it's more like our decision space is limited, but we work with potentially infinite amount of information. Our decision process, humans' decision process, or including animals, is to transform potentially infinite amount of information to limited space. We convert all the information that we find on a certain kind of product. Let's say I'm buying a mouse. There are hundreds of mouse out there. Brands, price, manufacturer, and quality. I look at others' reviews. I look at videos of test sessions, diagnosis, technical features, like noises when you click all of these information. In my brain, I will decide which feature is important. I assign a better weight. I assign a bigger weight. If I want a quieter mouse, I will discount those mouse that will make, clicking noises. I will not, buy a mechanical keyboard, of course, because that makes noises. But other people likes it. I don't like it. I like quieter, so I will assign a negative weight to the noise feature. But I like quieter, but I don't care. I may not care about wired. I can take wired. Some people prefer wireless. That's another feature. I'll consider that. After considering everything, I kind of have a net input in my mind. As long as it passes the threshold, I will buy it. In terms of, let's say, I have all the combination of features that I want, but it's too expensive. The price point literally, passes the threshold. I decide to not buy it, to look elsewhere. So so eventually it boils down to buy or not buy. And a buy or not buy is a binary decision choice based on all the information that I have thought about. That is a nonlinear decision process. And in terms of the model, it tried to implement the same concept. Question?
So if you have a very large data set with 3 attributes, then use one of these models. And so last semester we did correct every attribute and figured it all out and manually got rid of the level. So when they have people have many attributes, they skip that step and they just use one.
The principle remains. When you work with a bigger data set, one approach to going about machine learning model refinement is to better select variables. That's one approach. That approach would be more preferred if you're only working with linear models. Yeah, linear models have kind of a less of a capability to discount less important variables. Because the model is fairly simple. But if your tool set includes more sophisticated nonlinear models, and you feel comfortable working with that, then do less feature engineering, which means selecting inputs, comparing them, delete them, or exclude them. Do less feature engineering and give more flexibility to the model. That's a way of, deciding what to do. That makes sense? 300. Okay. 300 variables is certainly not large. We have like 1,000, 2,000, 5,000. Yeah, in business, there are certainly that kind of scenarios. But in those areas, the problems are even more complex. So we can talk about that later. So the activation process for Adaline, the activation is linear. So whatever the number becomes, it doesn't do any nonlinear transformation. But this is for pedagogical purposes. Later we'll replace it with something else. Okay, so here's the fun part. The optimization process where, also in activation, we'll calculate error. Error provides the kind of a pointer about how the model should update the weights. Error will be incorporated in the calculation of gradient. So you will see that. So let's talk about gradient. Gradient is the beginning of the optimization process where the model calculates the weight update. Gradient tells the model where, with respect to the objective, which is the cost function, where the model is currently at and how it should move toward the objective. That's what it does. In mathematical terms, it's calculating the derivative of a complex function, right? If you know what derivative is with respect to a variable, that's what it means. For intuition, let's say the model is simple. We have n, it can be anything, but we have m equal 1. What does that mean? We have one variable, but it doesn't mean we only have the bias. We do have the bias plus a variable. M is 1, right? So our data set looks like this. We have n rows, and we have one column, right? This is just one column of values. But our weight has two elements. The first one is bias. The second one, we call it W. Just hold on. W, just one single W, or W1, right? If we only have one weight, basically, to optimize the model, and the cost function, the W here, is really only referring to W1. It's not referring to bias. Bias as a part of the weights is kind of a passive weight. It's not an active weight that decides how the model performs. W0, which is the bias, W0 is kind of the remaining adjustment of the result of W1, sort of. It's more human language explanation. W1 changes, and then W0 changes according to the data. But W0 there is only for balancing the things. It's not there to decide how the model works. So this passive special component does not change how the model works, does not change how the model performs. So here in this case, if m is 1, we're actually only working with one thing that can change, that can decide how the model will work. Okay, so if we only have one weight, then what does this function look like? It looks like a hyperbole curve. W1 can potentially take any value in a real number line, and this cost function is like that. It's like that. It's not like this for a reason. Because this is sum of squared error, and it has to be positive, and it has to be convex, which means there is a dip point, but there is potentially, I don't know why it's not working. Okay, it can potentially become infinitely large. So that's the shape of that. And obviously, this weight location would be the optimal, right? If you end up with, if the value of W1 end up to be here, there's nowhere else that can improve the model, because the loss function has been minimized. You start from somewhere else by random number generation. You start from here, This is W1 owed as the first value. Okay, so the model used this value to calculate the net input and go through activation, which is nothing here, and make a prediction. At the same time, the model calculates the back propagation, which is by using this W and the activated value, it calculates the error, right? There's an error. Y minus activated value is the error, and then calculates the sum of squared error by including all the points, and then it lands to a value of the, this is the J. So its current cost is here. It should try to go that direction, right? And the best information we can calculate based on this cost function and the current value of W is the slope here. And the slope is what we call the gradient. And currently, the gradient is greater than 0 or smaller than 0? Which one? Is it greater than 0 or smaller than 0? Is it positive or negative? It's negative. So if we say delta W is the gradient, and we add delta W to delta W to W owed, will W new become larger or smaller? G is smaller than 0. Delta W is G, which is smaller than 0. If we add a negative portion to the owed W, which is here, will the new W be bigger or smaller? It will go this direction, which is farther away from the objective, right? So we have to revise this function to make it something like negative G. Does that make sense? Negative G is greater than 0, yeah? Because G gradient is smaller. Negative G is greater. You add some positive value to the owed W, it now, at least it gets closer to the objective. Yeah? That's a way weights are updated. You can calculate G fairly easily using mathematical tools. Computer can calculate that. As long as this function is defined, it's defined. As long as you know the W, you know the W. So you can calculate gradient. Once you know the gradient, you can somehow calculate the delta. Then you add the delta to the old weights, you get the new weights. Now the direction is no question. It should move that direction. It should move in the direction opposite to the sign of gradient. But the remaining question is, how much do you move? Do you move exactly the same as a gradient? That's a question. So oftentimes it's too much. If you have a G, let's say if the current weight is far away from the optimal value, the slope is going to be huge in terms of absolute value, right? It's going to be in a steep slope. If you move W by as much as the absolute value of the slope, it's going to get even farther away from the optimal. That's not good. So you need to kind of here to multiply something here that you choose. And complex models can optimize this part by treating this one as a dynamic feature where you can change it throughout the iteration process to adapt to early stage or later stage. But for now, we'll treat it as a fixed property. It's fixed. It's a value. It should be smaller than 1. Typically, it's in the range of 0 to 0.1. It's a scaling factor just to make it work. Right? Later, I'll demonstrate that, and video should also demonstrate that. So that is what the gradient process is. And why is a gradient descent? For one thing, it's trying to get to the bottom. That's gradient descent. This is a special case. We only have m equal 1. When you have m equal, more than 2, it's a higher dimensional space. You cannot really visualize what the slope is. But surely, when you have m equal 2, it's 2-dimensional slope. It's like a, but when you have more than 2 variables, it's harder to visualize. In higher dimensional space, if you think of, there's a point in the space which is at the bottom, so that's the way you will go. But once you have done the gradient descent, you have the gradient. You have the delta weight. You apply the delta weight to weight. You have the new weights, and you update the old weights, and that completes one process. The next loop will start with the updated weights and do the same thing. Throughout the process, what's changing? W is changing. Cost function is changing, and the gradient is also changing. All of these work in the same system, right? And weight update and update the weight. In weight update, we will do gradient. Gradient is just one step, but when we calculate the weight update, we do it in two-step process, similar to when we do the net input calculation, and we do it two-step, but it's not two steps, one step, but we do it differently for the two different kinds of weights. Bias is a special weight, the other weights are similar. When we do the delta weight, we calculate the weight update for the bias and weight update for all the other weights by using two different formula. This doesn't mean that they are really different formula, but in real implementation, it's easier to calculate, I guess. It's easier to, it takes less time overall for the computer to do following different formula instead of doing the same formula. It takes less time, it's more efficient. It just takes a little bit more time for human coders to implement the feature other than just using one generic formula. So computational efficiency is more important. Just by spending a little bit more time on coding, you get more computational efficiency when you implement the model. That's more desirable. But let me try to go through why these are the same thing. So according to the notes, gradient is calculated by minus sign times eta, the learning rate, times the gradient. You calculate the gradient, and that's the formula. So you will calculate all the other weights by following the formula. But when you calculate the weight update for the bias, we're using a different formula. And how to see that they are actually the same thing. So this is delta weight, beginning with index 1, is minus eta gradient. So let's say G depends on W, okay? And in actual formula, it's minus transpose T dot error. So that's how you calculate the gradient term for all the variables. So to imagine what a gradient is, it's a vector of length equal to the number of weights. So if there are m plus 1 elements in the weight vector, there will be m gradient. Should there, let's see, gradient. I think that's not right. The length of gradient should be the same as m. There are as many as m gradient terms for the m weight elements. There is no gradient for the bias, because the bias term need not be optimized. Okay, so that's right. And the gradient is different for each of the specific coefficient. All right, so that's a generic formula for calculating delta weight. And when we say the delta weight for the bias, we can think of it as the same process, as if we have x here. Let's say we have x0 for the bias, and we transpose and times error. The error is the same. Okay, so now the concept about linear regression is useful. In the terms of linear regression, is we typically use beta plus beta 1 times x1 plus a bunch of terms plus beta m xm. So when we write the typical regression equation, all the terms are multiplication except for the intercept. But you can imagine the intercept term is also a multiplication, but it's being multiplied by something of a constant term, right? And you can say it's constant term of 1, which is doing nothing. But you can imagine the x associated with intercept is 1, and it's fixed. There's no change. So applying that concept to here, this formula becomes negative a column vector of 1, and you transpose it, which is you make it a row vector of 1 of 1s. And you multiply that with error, and there should be an eta here. Should be an eta gradient, or I think I'm missing a negative sign here. Let me revise that. Minus eta times, and the gradient part also have a minus term. right? So that's why there are two minus, but we don't really unpack this parenthesis because we already calculated gradient, right? So we simply use that. But when we do the bias term, we cannot apply gradient result because gradient uses those x's that are not related to bias. Now we're calculating bias. But we imagine if there's x, those x's are 1. So we unpack x's to be a factor of 1s. And here I have to copy that. So that's what it really is being calculated. And if we multiply a row vector of 1 with a column vector of something, it's essentially calculating the sum of that column vector. Why? If we have a row vector of 1, we multiply that by column vector of something, it's 1 by something, n, it's actually n, because there are n data points. And now it's n by 1. The result is a scalar, 1 by 1. And the way you calculate is you multiply the first elements, multiply the second elements, and do the same thing, and then add everything together. If you multiply everything by 1, it doesn't change. And in the end, it's only adding everything together. So this step becomes minus eta minus the sum of error. And the two negative signs cancel out. It becomes eta times error, the sum calculation. And that's why the notation says error times sum of eta times sum of error. That's why. That's why calculation is different, but they are actually doing the same thing. All right, so once we have these, update the weight. It becomes a new, and this is where I print out the old and new, and this is where you can actually do the debugging process. If something didn't go well, if the result is not what you expected, you can go back to this point to check what is the new O, what is the new W, what's the old W, and is that delta W, equal to their differences. So that's why we do that. Instead of simply update the W old equal W old plus delta W, that would be direct overwriting of the OW, and there's no way to debug, I guess. So that's why we do it a little bit tediously, but for a good reason. So that's the end of the loop. If you put everything together into a for loop for the number of epochs for loop, then the weight, the old weight will be continuously updated. But whenever you do this, don't forget to rerun the initialization process to randomly draw the coefficients, because you have already done a for loop. I mean, you have already done one loop process previously, so you don't want to start with a middle point. And in the end here, it also calculates the cost. Cost is sum of squared error, and you can refer to the notations. Here, there's not too much point. And the point I want to talk about, to highlight here, is when I have eta of 0.01, I have eta of 0.01. What's eta? Learning rate. It's the term that you multiply with gradient to calculate the delta weight. So that's critical to weight updates. If we have 0.01 and we have the entire data set is already standardized with Z standardization, And even that, when I calculate the cost is supposed to be smaller over time. When I calculate the cost, I print the cost values. It goes from 9.3 times e to the power of 1, which is 10. Here, e is the 10 base. So it goes from 93 to 56,000 to 1 million and to exploding. So what does that mean? That means the weight update is jumping farther and farther away from the optimal point to the point that it explodes. This, how I can't say how large the number is. It's just, it's not right. So to make it right, you revise the learning rate to something much smaller. You know, this is much smaller. This is 50th of the original value. And when you do the same thing, the cost function reduces from 93 to 31 after 10 epochs. That's a curve you want to see. You know, so that's right. And typically, you don't need that small learning rate, 0.002. You don't need that small. This is small because this is Adaline. Why is Adaline more picky? Because there is no nonlinear transformation, nonlinear activation in the middle. It works with the raw input. It's a raw input. If the weights are too big and the learning rate is not small enough, it will linearly explode. If you have a nonlinear activation process to squeeze the values in a tight region between 0 and 1, this would be less likely to happen. So that's why when you do the codes, when you run the follow tutorial on logistic regression, when we have a sigmoid transformation and you use the old learning rate, which is 0.02, it's fine. That's why logistic regression is fine. I think I've covered all about Adaline. Any questions about that? Megan? Which part? Go ahead. Maybe this one?
Initialize, you run the loop, and my loss function numbers don't look good. It's too big again, so I ADA, so it moves slower down the curve.
Yes.
Then say, okay, now I'm rerunning it with a smaller ADA, and my loss function looks good. I like the curve now. Then what do you say? Now I'm going to manually change my number of.
Then I stop there. For Adaline model, it stops here. If you see the curve like this, you run a few epochs, right? You run 10, which takes a little time, and you see the curve of that cost function. This is a good sign. It's reducing with slower rate, but it's supposed to happen. It will keep reducing. So what to do now? You increase the epochs. You increase the number of loop repetitions. Huh? Why? Because you want to let the model keep training for longer time. Yeah, yeah. And then it stops there. You know, you stop at one point. And that is where you know, evaluate the model on accuracy. So that's model evaluation. Right. Typically, you don't have to change too much times. The number of epochs where you stop is part of the evaluation process. And we'll talk about that later. Today is more about the learning process. and to see the difference between Adaline and logistic regression. That's the difference. So let me switch gear back to talk about homework. And this is more of a here. I don't know if it's included in your slides, but maybe I'll talk about it next time. So that's one thing. The other is logistic regression sigmoid transformation. So here, logistic regression, and when we do Z, it's the same. The data object is slightly different because the naming differences. Formula is the same. Activation now changes. The change essentially is here. For now, you can ignore Z clip. So imagine Z clip is Z. Z is the net input. So when you have the Z, instead of multiply that with 1, it will do a follow-up formula. And that formula is this one. You'll follow this formula and translate it to Python code. It's that code in the demonstration. This is the sigmoid transformation that transforms any value on the real number line into values between 0 and 1 to squeeze it into a tight region, which is an S shape. And if you translate this formula to Python code, it is like that. 1 over a big parenthesis. Inside the parenthesis, which is the denominator, it's 1 plus the, exponential of the natural number, and the exponent is minus Z. And there's a special step here, Z clip, which you can feel safe to ignore, but you can follow the step exactly. And the purpose for that is simply just to prevent the unlucky event where you happen to generate random coefficients that are super large, which can make the Z value exponentially large. If that's the case and you don't clip the extreme values, calculation will be a little bit slower. But I wouldn't imagine for any of the laptops that we have here will have a problem. So you can safely skip that, or you can copy that exactly. So that's just a technical trivia thing, okay? But with that one more step, it introduced opportunity for typos. So be more careful when you try to implement that. Make sure you don't have typos, and make sure you get the code exactly the same. That's it. That's it. You should be able to do the homework at least, except question 8. Okay. So it will require you to watch the video carefully and try with the sample data set, the insurance data, the financial data set, credit cards, and then adapt the codes to the homework data sets where the ID column is different, right? It's phone, not ID. The target is different, it's churn, not default. And all the other variables are different, but it should be the same logic. Okay, let's call it a day. And let me know if you have any questions.